Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue working in supervised learning. In this particular video, we'll look at linear models and begin talking about ordinary least squares. So these are the items we'll cover. What are linear models? Then what is ordinary least square? A linear regression, and then we'll look at an example to get an intuition of all how that works. And finally, we'll get into Jupyter Notebook and look at how we can implement linear regression using scikit-learn libraries. Here we have these features which are x1, x2, x3 all the way up to xp, and they are all linearly related, as in the parameters that join them are w0, w1, w2, w3 up to wn, as they are shown here as well. So all these parameters, they are linear because they are not they are not raised to a power of, let's say, 2 or 3 or anything. So they're just raised to power of 1, all of these. And y would be the predicted value, which is based on the parameter w and the feature x. And here the w0 is the intercept. So if we look at just one feature where we just have x1, then we have a very simple equation which would be y is equal to w0 plus w1 into x1. So there w0 would be the intercept and w1 would be the slope of the line that is plotted. Now let's look at a concrete example where we have two features, x1 and x2, and these are the values for those features, and then we have a target value y that is shown here. And in linear regression, what the idea is, it is to use this set of feature values and the target values and find the values for the parameters w0, w1, and w2. So when we fit the model, that's what the program is doing in the background. It's trying to calculate the values for w. And after we get the values, let's say we get the values of 1 for w0, 3 for w1, and -2 for w2. We can plug those in back in this equation. So we get this equation: 1 plus y is equal to 1 plus 3x1 minus 2x2. Now this equation can be used to calculate the predicted values by plugging in the values for feature 1 and feature 2, that is x1 and x2, in this equation. And when we plug in the values, for example, x1 is 0, x2 is 0, so we plug in x1, x2 as 0, and then we calculate the value is 1. And similarly for all the rest of the equations. And in this case, it so happens that these predicted values are exactly the same as actual values because I chose the example in that way. But in reality, that would not happen. What will happen is the predicted value would be a little bit far off from the actual values. And we'll talk more about that in upcoming slides. So that difference, uh, what ordinary least squares does is it tries to minimize the difference between the predicted value and the actual value. And to do that, it uses least squares cost function, which is equation that is shown here. So the double lines just mean that it's in a matrix form, and minimizing, we are minimizing w in this case. And what this is sum of squares. So xw is the predicted value that we calculate from this equation, and y is the actual value. And the minus sign just tells us that we are taking a difference between those two values, the actual value and the predicted value, and then we are squaring that up. Now to calculate the parameters w from this equation, if you derive the ordinary least squares, I'll end up with this particular form, matrix form as shown here, which is x transpose x, inverse of that multiplied by x transpose into y. And this gives us a matrix of parameters w, and those would be same as what we have here. And that's how ordinary least squares can be used to calculate or estimate the values for the parameter w. Now, here's a concrete another example that we can look at. Uh, we have the values x and y, so we are considering only one feature, which is x. Y is the target that we have, and so what we are doing is we are calculating the sum. So x, the sum of x, sum of y, and then these three columns are x square, xy, and y square. So 1 square is 1, 2 square is 4, and then we add them all up, we have 220. Similarly, 1 into 2 is 2, 2 into 1 is 2, and then we add all them up, it is 219. And finally, for y square, we have 2 square is 4, 1 square is 1, and so on. And then we add all those up as well, and we get a value of 231. We then use these values to calculate the sum of squares for x, which is we subtract each value in the column x by its mean, and then we calculate sum of squares y. So we subtract each value in the column y by its mean, and then square them up. And similarly, we calculate the sum of squares xy as shown here. So we subtract each value from x, subtract each value of x by its mean multiplied by the value which is from column y, where we subtract each value from its mean. So here y is the value and y bar is the mean, x bar is the mean, x is the value. So let's say here we'll have x minus x bar, means it's 1 minus the mean of this column, and then we square that. And then finally the summation tells us that we add all those squared values and we end up with 54. So that's how we calculate all these values. And then to calculate the first coefficient b1, we take the ratio of sum of squares of xy divided by sum of squares of x, and we get the first coefficient 0.8932. And similarly for b0, we use this equation to calculate the coefficient, which is 0.6614. And those can be plugged in into this equation, which is linear equation, and we have these final values that are calculated. So that was one manual way of calculating the coefficients. When we minimize the least squares, we do exactly the same process in this way, where this equation gets transformed into this equation that is shown here, which is 1 over x, sum of squares of x. And then here we have this matrix where we have mean of y into sum of squares of x minus mean of x into sum of squares of xy divided by sum of squares, not divided by, and in the second row for this column we have sum of squares of xy. And if we plug in the values from this previous slide in this one, we get exactly same coefficient in the output. So we have w0, which is the first row, and then w2, w1, which is the second row. So that's how we can use this equation right here to calculate. We can minimize that equation so that we find the smallest possible values for the parameters that we can use to predict the values of y for any given value of x. Now, in the past slides, we talked about uh, the difference between actual and predicted value. Here is an example visualization of that. Let's say we have a feature x and we have an output y, and the green dots show the actual data points. And if we fit a model, which is shown by the dotted line in here, then that dotted line represents data points that are predicted values. Now, those are shown here. So let's say this particular green dot is the actual value and its predicted value is down on that line. Similarly, for this particular data point, the predicted value is down here, up here. So there is a difference between the actual value, this, and the predicted value, which is shown by this red line. And that difference is called residual. And when we say residual sum of squares, what we mean is we take the square of this particular value, the difference between these two. And that's exactly what we have in here. We are taking the difference between the values, and that's what we are doing right here, and squaring all those values together. So the goal is to find a line that passes through these points such that this difference between the actual and predicted for all the points combined together is as small as possible. Now, here is another example. Uh, so this is a little bit counterintuitive, that this is also a linear regression, given that the line that is fitted is not linear, it's a polynomial. The reason is because uh, the reason why it is linear regression is because the parameters are linearly uh, uh, connecting the features. So x1 and x2 could have power of 2 or 3 or 4. However, the parameters that uh, join these features, they do not have any power, so they are linearly placed in that equation, and therefore this is also an example of least squares where we can use linear regression to fit this polynomial, and will see that uh, in upcoming videos as well. Now, in Scikit-learn, when we perform linear regression, there is also an option to get positive coefficients for the fitted model, and that's sometimes useful if you're looking to get only positive coefficients in the output. Finally, in this code snippet, this shows us the format of implementation. We have imported the linear model library, and these are the train and test set we have. So we first initialize reg using linear model dot linear regression, and positive is set to false. That's the default. And then we fit that to the train dataset, and then use that to predict the uh, uh, test using the test dataset. So let's now get into Jupyter Notebook and see how we can implement uh, ordinary least squares. Here I've imported NumPy library, and we do not need the pre-processing, so I'm going to change that to linear model. And we additionally also need the plotting library, so matplotlib.pyplot splt, and these are the versions for Python. Now for data, I've created these three uh, sets. So we have the first one, which is this array. Then we have the second set of data, and finally we have the last set of data right here. Now let's see. There is a comma needed. Okay. So that's the final set of data we have. The first example we look at is using only one feature. So example number one, here we are going to use only one feature. And for this, we'll use the data set called data. And what we are going to do here is we'll create variables xtrain, and within xtrain, we'll put the first column. So we'll call this a feature, and then the second column we'll call that as a target y. So from data we'll choose the column all rows and column 0, and we'll reshape that because the linear regression model expects it to be in this form. And then we'll create another variable y train. Again we have data, and we'll use one second column, and again reshape that in this particular form. Now once we have that, we use create the initialize the variable reg, and then we have linear underscore model dot linear regression regression. And once we initialize it, we need to fit the model, so we'll fit it to x underscore train y underscore train. And once we are done with the fitting, so that's the fit. And once we have fitted, we can actually go ahead and look at the coefficients of the uh, fit model. So here we have the coefficient is 0.89, and we can also look at the intercept. So that's so sorry. Okay. So that's so here we have the intercept and the coefficient calculated. So now we can go ahead and predict a value. So for prediction, we could use the train set that we have. So let's say ypred is equal to reg dot predict x train. We could use a new set of data using test, but I'll just go ahead and use the x train. Now we have the predicted value. Let's now see how the data looks when we plot it. So plt dot scatter x underscore train y underscore train, and then plt dot. So that's our first data set. That's the original one. On top of this, we'll add the predicted values. So x underscore train y underscore pred, and we'll put them in red color. So those are the predicted values. And why don't we also go ahead and add a line to those? So I'm going to change that and say this is plot, and maybe give it a gray color. So that's our predicted model that we fitted to the data set. And so here plt.x label, this is x, and plt.y label, this is our y, which is the output. So as you can see, the predicted values are a little bit far off from the actual values in all the cases. And that's what we saw in the slide in the presentation, where these were connected by red lines, and that shows that there is a residual between the actual and predicted values. Now we can go ahead and uh, look at the score of these. So that's the r square value. How good is the fit? So higher the value, the better it is. So if we look at the score x train, y train, you get a score of 0.78 in this case. Now moving on, we can do some manual calculations. So manual calculations, and this is just to give you a clear intuition of what's actually happening in the background when we are trying to minimize that cost function. which is what we saw in this equation. So we can calculate all these values that are shown here. And to do that, what we'll do is, let me go ahead and create cells here. Okay, so let's create a variable x, and I'll make a copy of that because it's easier to type x and y instead of x train and y train. Okay, so we have those created. Now, based on the equation right here, first what we need is the sum of x's and y's, and then we need the square values of x's and y's, and also the sum of xy. So we'll go ahead and calculate those now. So x underscore sum is equal to np dot sum of x, and then we have similarly y underscore sum is equal to np dot sum of y, and we have x square, so we are going to get sum of that, np dot sum, and this is x square, and then we have y square, so y square is equal to np dot sum, and we have y squared, and finally we have xy sum, so xy sum is equal to np dot sum, and then we also have to multiply, so np dot multiply x and y. So these are the values we calculated. The second set now is these values. So we want to calculate sum of squares of xx, yy, and xy. So let's do that. Sum of squares of xx is equal to, we first need to get the difference. So x minus np dot mean of x, we get that difference, and then we want to square the values that we get, and after we square the values, finally we need to add them, so we take the sum of that. And similar to this, we need to calculate the values for y, and so that's what I'm doing here. Subtract each value from the mean of y, and finally we have the sum of values for xy, and in this case we have no sum here, but what we have is x minus np dot mean x, so we subtract each value in column x by its mean, and then after this we multiply this with the same method, y minus np dot mean of y. So we have all these values calculated. Now we need to calculate b1, which is sum of squares of xy divided by sum of squares of x. So b1 is equal to ss underscore xy divided by ss underscore xx, and then we have b0 is sigma sum of y divided by n. So b0 is equal to y sum divided by n, and here let's create n is just the length of x, so we have that set there. And now, and the next one is minus b1 into sum of x divided by n, so minus b1 into x sum divided by n. So that's how we have all these values calculated, and let's go ahead and print this out. So print, we are going first need the b1, and after b1 we need to print the value of b0. So b0 is here, and we get the values, which is 0.8932 and 0.6614, and those are exactly the values that we had before, 0.8932 and 0.6614. So that's good to know that uh, how the ordinary least square works to calculate the coefficients for uh, given data set. Secondly, we can also go ahead and calculate the values for this particular case where we have this equation right here in the middle. And to do that, we'll use the values that we calculated above. So manual calculation number 2, and here we will use the same formula that was on that slide. So it is 1 over sum of squares of x, so ss underscore xx, and then we have now this is an array, so we need to create an array there into np dot array, and the top row is this difference, so mean of y into sum of squares of x. So np dot mean of y, we already have calculated that up there. No, so let's go ahead and do that. Np dot mean of y my into sum of squares of x, and then we have np dot mean of x into sum of squares of xy. Okay, I think yes, and then we have sum of squares of xy in below that. So sum of squares of xy, and when we run this, we get the values for coefficients. We have w0, which is 0.6614, same as before, and we have w2, which is 0.8932, again same as what we had before. So that's awesome. So we tried to calculate the coefficients using ordinary least square for examples with 1 and 2 features, and those sorry, just one feature, by using 2-3 different perspectives. Now let's look at how we can work with 2 features. So in this example, let's call this example 2, and here we'll use 2 features to calc and see how we can work with this. Now for this one, we'll use the xx and yy. So we'll use this data set, and for this, to fit the linear regression method is the same. So we'll create a variable reg is equal to linear underscore model dot linear regression, and here we'll use, we can do a dot fit here, or we can say reg dot fit, and here we specify xx yy, and then we can get the score, which is the fit score. So print reg dot score, and here we can say xx yy again, and it's a complete fit, because we also saw this in the slides that all the predicted values matched the actual data set, and that's why we are getting 1, but that may not always happen. And finally, we can look at the coefficients. So reg dot coefficients coef, and that's 3 minus 2. And if you remember, in one of the slides we looked at the values for these coefficients, which was right here. So we have these had 2 features, so 3 minus 2, and then the intercept was 1. So let's look at the intercept, reg dot intercept. So we are close to 1 here in the intercept as well. So it's the same data from that slide that we are working with here. Now we can also try to predict. So predict, and here we need to give information in array format. So we give points 12 and 13, and the predicted value is 11. Now we can try to calculate that as well. So our equation would be y is equal to w0 plus w1 into x0, and then we have w2 into x1, right? Or we can say this is x1, and we have this second feature x2, and the plus C. So if that's the equation, here we can say W0, which is our intercept, is 1 plus, uh, then we have, so we don't need that, we already have W0, 1 plus W1. So in this case, we have W1, which is 3, and into X1. So X1, we have 12, and then minus, because okay, we can do plus there, in within parentheses we have minus 2 into X2, which is 13. So when we run this, we get a value of 11. So that's how the intercept is used in the predict to calculate the predicted target value, in this case, which is the value of y, and that is equal to 11. Now let's look at a third example where we can suppress the values, or uh, limit the values of coefficient to be only positive and not negative. Example number 3. And here we'll use the x and y, which are, let's see, okay, so this needs to be equal to, let's run this again. And so we have the x and y values. Now we can uh, create the variable reg and then initialize it. Model is linear regression, and here we'll specify positive is equal to true, and then fit this on x and y as we have above. Now when we look at the coefficients, so reg dot coefficients, you can see that they are all positive coefficients. And on the contrary, if we take the same uh, line of code and change this to false, and now if we run reg dot coefficient, we see that there are negative coefficients. So we have -5 right here, which is the first coefficient, and here there are no negative coefficients. Now you'll probably wonder, does that affect what the predictive value is? And it does affect. So let's put this here. And the prediction accuracy may suffer because of this. If you type, uh, let's look at reg.score, in this case x and y, and as you can see the score is 0.56, and here if we look at the same score where we have set it to false, the score is much higher. It's full 1. And so setting the value, if you need a model to predict only positive coefficients, then this could be this is something to keep in mind, that could affect the accuracy of how good the fit would be. So it may not be uh, a better fit as compared to when you'll have the coefficients that are negative as well in the model. So that was it for this video. I hope in this video you learned what are least squares, what is the intuition behind least squares, and how we look at the residuals, that are the differences between the actual and predicted values, and how we can manually calculate these coefficients, how we can use the linear regression method from the linear models in scikit-learn to calculate the coefficients. And in next video we'll continue working on linear models, and we'll look at other uh, scenarios where we add regularization parameters to the optimization or cost function that we saw in this video. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.